You were responsible for all the different calculations we did this semester in laboratory for the final. The only ones you're not responsible for are the library assignment. There will be nothing on that. Safety, nothing on safety. And also experiment 25, that is the qualitative experiment where we had that long flow diagram. That one's not on the finals either. But the rest of them, there will be problems similar to the type of calculations we did in lab. Let's start off with the first experiment we did, which is the acid-base titration, which was done with a new term called normality. Calculate the normality of a 10 milliliter solution of sulfuric acid if it requires 15.2 milliliters of 0.305 normality of sodium hydroxide to reach the equivalence point. The nice thing about normality is that it's mole-to-mole ratios within the actual substance itself, that concentration of that unit of normality, so we don't have to write a balance equation. What we do to do these type problems is simply follow our dilution calculation, except that it's done in normality units, which looks something like this. Normality of your acid times the volume of your acid equals normality of your base times the volume of the base. So in this case, if we look what we ultimate goal is the normality of the acid. So I have to rearrange this equation to solve for the normality acid, which basically means I need that volume of the acid to basically be divided on both sides, which then gives us normality of the acid is equal to normality of the base times the volume of the base divided by the volume of the acid. We did this calculation to do the standardization part of our sodium hydroxide, which we sent, in that case we're solving for the normality of the base, and then we went back and did an unknown acid, which is kind of like this calculation where we're determining the normality of that acid. So now all you do is just plug in those variables. So for the normality of the base, we have 0.305 normality of sodium hydroxide. For the volume of the base, we have 15.25 milliliters of sodium hydroxide, and the volume of the acid was 10.00 milliliters of sulfuric acid. It doesn't matter the units when we plug in here, as long as we got the same. That way they cancel, so milliliters cancels with milliliters, leaving us in normality, which is what we're looking for. And you multiply that out to get 0.465 normality of sulfuric acid. And then make sure that you do the correct significant figures. In this case, the 0.305, which has 3 sig figs, is limiting our answer. Since this is all multiplication division, it goes by the least number of significant figures of the number in that calculation. Next experiment we did had to do with the hardness of water, where we calculated the titer of our calcium carbonate. Okay, this is a ratio of milligrams of calcium carbonate per milliliter of EDTA solution. So it's a ratio between two substances. It was our standardization step. We figured out this titer. Once we knew the titer, then we could calculate some unknown water, the hardness of that water, and a hardness scale in ppms of calcium carbonate. So this is an example of how we calculated the titer. Calculate the calcium carbonate titer for an EDTA solution if it requires 20.8 milliliters of EDTA to reach the titration endpoint with 50 milliliters of 0.01000 molarity of calcium carbonate standard solution. And the molar mass of calcium carbonate is 100.09 grams per mole. So basically in this problem, we're starting off with some standard solution, 0.01 molarity of calcium carbonate and 50 milliliters of it. If I multiply moles per liter times my volume, then I get moles. Okay, our goal is to get to our milligrams of calcium carbonate per milliliter of EDTA. So my goal right now I'm looking at is how can I get to milligrams of calcium carbonate? Well, we have a molarity. I got 0.01 molarity solution of calcium carbonate. I also know the volume. So if I multiply volume times molarity, then I get moles. Okay. In this case, my ultimate goal is milligrams, so I'm going to cancel my liters, but I'm leaving that prefix of milli there. So right now I'm in millimoles. Okay. If I multiply 0.01 times 50, right now I'm in millimoles of calcium carbonate. My goal is milligrams, which is a mass term. Well, how do I get from moles to grams? We do that through molar mass. So I'll multiply next will be my molar mass. So I have 100.09 grams of calcium carbonate for every 1 mole of calcium carbonate. In this case, you see my moles cancel. So now my milli is part of that gram. So if I multiply my molarity times my volume times my molar mass, what I have right now is milligrams of calcium carbonate, which is the numerator part of this equation. Now I need to take that whole numeric number and divide that by the volume of EDTA. So my next step will be to multiply that by a factor of 1 over that volume. Okay, so basically dividing by the volume. So I end up with milligrams of my calcium carbonate. Okay, so all this gives me milligrams of calcium carbonate over my milliliters of EDTA. I multiply that out. I get my titer, which is 2.406 milligrams of calcium carbonate per milliliter of EDTA. Significant figures in this problem, the least was 4, so I should have 4 in my answer. Now, the important thing in this one is when you report the answer, you must have it as milligrams of calcium carbonate per milliliter of EDTA. This is a ratio of 2 different substances. You must write those substances. Okay, you must write that in your final answer because it's a ratio of 2 different substances. Then once we had the titer, we took that, since that's a standardization of how much calcium carbonate per every milliliter TA, and we took that and did that to an unknown sample of water to figure out the hardness. So we basically take our titer, which in this case we're saying it's 0.7745 milligrams of calcium carbonate per milliliter TA, so that was a calculation done before. Okay. Then we did that against our water, which took 26.60 milliliters of EDTA. Okay, we had a 50 milliliter water sample. I want to figure out the ppms of calcium carbonate. So the starting point in this problem would be our titer. Okay, I know there's a ratio, 0.7745 milligrams of calcium carbonate for every 1 milliliter of EDTA. So if I know how many milliliters of EDTA I have, then that would tell me how many milligrams of calcium carbonate is in that unknown sample. So my next step would be to multiply by the volume of EDTA it took to get to that equivalence point. In this case, it was 26.60 milliliters of EDTA. My milliliters of EDTA cancels, so right now I'm in milligrams of calcium carbonate, which is important because for ppms, you may recall, is equal to milligrams of calcium carbonate per liter of water sample. So our goal here is to get it in milligrams of calcium carbonate per liter of water sample. So presently I have my milligrams of calcium carbonate. So all I got to do now is divide it by my liter of water sample. Well, it gave it to me, I got 50 milliliters of water. It's not milligrams per milliliter, it's milligrams per liter. So the next step is I'm going to have to change my milliliters to liters. And my milliliters cancel. So now I have milligrams of calcium carbonate per liter of water, which is what I want. Okay, multiply this out. I get 412.03 milligrams of calcium carbonate per liter of water. Now 2 more things we got to do to get an answer. I want the correct sig figs, and also they ask for it in ppms. They ask for it in ppms. ppm is a milligrams per liter, so I'm going to change that into ppm, so 1 to 1 between those. And my final answer is 412 ppms of calcium carbonate. 3 sig figs coming from that water, 50 milliliters, which is 3 sig figs in that. 50.0 is only 3 sig figs, and everything's multiplied and divided, so it's going to go by the least number. Another calculation we did was going from normality to molarity. Okay, we did this when we did the redox experiment, so it's important to be able to do that. To go from normality to molarity, or vice versa, you need to have the half reaction, because we need to find out how many electrons are in the balance equation. That number of electrons gives me that ratio of the number of equivalents per mole of a substance. So, and our goal in this one is we want to go from normality of 0.3 molarity. We want to calculate the normality of a 0.3 molarity solution. So I want to go from 0.3 molarity to the normality of a substance. You may recall normality is equal to your molarity, moles per liter, time your number of equivalents per mole. That way your moles cancel and you're left with number of equivalents per liter. Well, where do I get my number of equivalents per mole? That comes from my balance equation. My balance equation, I see I have 3 electrons. That tells me my number of equivalents per the different substances. H plus is there's 3 equivalents per every 4 moles of H plus. There's 3 equivalents for every 1 mole of nitrate. 3 equivalents per every 1 mole of NO. 3 equivalents per every 2 moles of H2O from the balance equation. Well, we're looking for sodium nitrate. Okay, so I want to compare that to the nitrate. So that tells me I got 3 equivalents for every 1 mole of nitrate. And how is nitrate related to sodium nitrate? Well, there's a 1-to-1, which basically means then there's 3 equivalents for every 1 mole of sodium nitrate. So to do my calculation then, I'll start off with my molarity. I have 0.3 moles per liter of sodium nitrate. What I want to do now is convert that moles into equivalents by using my number of equivalents per mole, which we just said is 3 equivalents of sodium nitrate for every 1 mole of sodium nitrate. My moles cancel. So now I'm left in equivalents per liter, which is the unit for normality. So this is 0.9 equivalents per liter of sodium nitrate, which I'll convert to a capital N, which is a symbol for normality, which gives me an answer of 0.900 normality of sodium nitrate. The other thing that we did in the redox experiment is balance and redox equations. So here's a molecular equation that we need to balance. Okay, notice there's a lot of oxygens in here. Almost every substance has an oxygen, so it's a little harder to balance this by just doing it by inspection. So what we're going to do is balance it by redox methods. So the first thing I want to do is get rid of the spectator ions. So let's look at it. I got sodium chloride. Now let's look at that and see what happens to sodium on the other side. It turns into sodium perchlorate. Solubility rules. The sodium is a group 1, so they're going to break up into ions. So I got sodium ions in both cases there. So I got Na plus on one side, Na plus on the other one, and Cl2 minus and ClO4 minus is different. So what we have is sodium is a spectator, so I'll get rid of that. Okay, other spectators I got, let's look at potassium permanganate. That's a soluble salt. Potassium is a group 1. On the side, it's part of potassium hydroxide. That's a strong base, so that's going to break up 100%. So once again, potassium is an ion floating around, so that's a spectator. Water stays as a whole there, so basically that's all my spectators. So if I bring down everything, my net ionic equation will be my chlorite plus my permanganate plus water gives me manganese 4 oxide plus my perchlorate plus hydroxide ion. And the hydroxide ion is telling me that we have a basic solution, which means I have OH minus and water at my disposal to balance my hydrogens and oxygens as needed. The next step is to figure out what's being oxidized, what's being reduced. Well, if you look at it, you got chlorite going to perchlorate. Okay, that's a case of gaining oxygens, which is an indication that that's an oxidation. Also, the chlorine charge is going from a +3 to a +7. That's an oxidation as well. So that's my being oxidized. And then I got to figure out what's being reduced. I got MnO4 minus going to MnO2 with no charge. Once again, this is losing oxygen, so therefore that's a reduction. Or look at the charge, it's going from a +7 on your manganese to on this one, if you balance it out, that's a +4, and that's a reduction in charge. It's going from a higher charge to a lower charge, therefore that's a reduction. You need to be able to pick out what's being oxidized, what's being reduced. After we figure out what's oxidized, what's reduced, we have to balance the atoms. Okay, so if we go through this, let's do the oxidation first. You can see I got 1 chlorine on both sides. That's not a problem. But then I got 2 oxygens on one side and 4 on the other. So there's no way I can balance that by just putting a coefficient. So this is where the OH minus in water comes in. Since I need 2 oxygens and hydrogens are not an issue here, we said what we typically do is say, okay, I need 2 oxygens on my reactant side, so I'm going to double that and put half as many waters. That way my hydrogens stay balanced. So in this case, I will add 4 OH minuses to my reactant side and 2 waters on the product side. And notice now everything's balanced. I have 4 oxygens, 6 oxygens on both sides. I have 2 chlorine on each side, and I also have 4 hydrogens on each side. So all my atoms are balanced. I'll do a similar thing with my reduction. Once again, manganese is balanced on both sides, so all I need is oxygens to fix. I can see I need 2 on the product side, so I'll add 4 OH minuses to my product side and half as many waters, which would be 2 waters on the reactant side. And this is now balanced in atoms. I have 4 hydrogens on both sides, I have a manganese on both sides, and I have 6 waters on both sides. 6 oxygens on both sides. After we balance the atoms, what's next? Got to balance the charges. And the only way we can balance charges is with electrons. Okay? Electrons, you realize, are -1 charges. So that's the only way I can balance them, is using that. Let's look at the oxidation. What's my total charge on the reactant side? Well, I have 4 minuses and a minus. Okay? Well, if I got 4 minuses and a minus, that's a total of 5 minuses, right? On the product side, I have 2 waters, which is neutral, so 0, and I have 1 perchlorate with a minus charge, so that's a -1. So I need to balance that 5 minus and the 1 minus, and the only thing I can use is minuses, which is the electrons. So how many and where am I going to add it? Well, if I need to balance it, I'm adding negatives, it's going to have to be on the product side, and it's going to have to add 4 of them. Notice if it's oxidation, the electrons should be on the product side if you're doing things correctly. So in this case, we know we need to add 4 electrons on the product side. For the reduction, let's see what we have for our total charge on our reactant side. You have 2 waters, that's neutral. I got permanganate, I got 1 of those, so I got a -1. And on the product side, I have 4 OH minuses, that's 4 minus. And the MnO2 has no charge, so I have a -1 and a 4 minus. I need to balance that. The only way I can do it is 3 minuses on the reactant side, which we know reduction means take on electrons, so it should be on the reactant side. And in this case, it's going to be a case of 3 electrons on the reactant side. So now I have my half reactions balanced with electrons and charges. Now I need the whole reaction to balance. You can see my oxidation produces 4 electrons, and my reduction takes on 3 electrons. That's not balanced, so I need to do something to balance that. So the simplest thing is the common denominator here. So I'll multiply the oxidation times 3 to get 12 electrons, and I'll multiply the reduction by 4 to get 12 electrons. When I do that, the number of electrons will cancel out. So I'll multiply the oxidation by 3, multiply the reduction by 4. When that happens, my 12 electrons will cancel out. And then I got to multiply the factors through and bring them down, which means I have 3 times 4 OH minuses, which is 12 OH minuses. I have 3 times my chlorite, which is 3 chlorites. I have 4 times my permanganate, which is 4 permanganates. I have 4 times my 2 waters, which is 8 waters, 4 times my manganese 4 oxide, and 3 times my perchlorates, and I have 4 times my 4 hydroxides, which is 16 hydroxides, and I have 3 times 2 waters, which is be 6 waters. So this is my balanced net. When you get to this point, we need to make sure we can't reduce it any further. Is there anything in common on both sides that I can reduce it or multiple or divisible by some common factor? If they're all even numbers or all odd numbers, it should be divisible by something, and you can reduce it that way. But if you have odd and even numbers, then no, it shouldn't be. But let's see if there's anything in common on both sides, and we can see I have 12 hydroxides and 16 hydroxides. Well, 12 of them are canceling out each other. That leaves me a net 4 OH minuses on my product side. And is there anything else? Yes, waters. I have 8 waters and 6 waters. That leaves me a net of 2 waters on my reactant side. If I bring this down, that gives me 3 chlorites, 4 permanganates, 2 waters, 4 manganese 4 oxides, 3 perchlorates, and 4 hydroxides. I'm still not finished yet because I took spectators off. So I got to put the spectators back on. So for the chlorite, the spectator was sodium, so I'll put that back on. Notice it's a 1-to-1, so it's not going to change my coefficients. For the permanganate, it is potassium. Put that on, it's a 1-to-1, so that's not going to change my coefficient. The perchlorate, once again, that's sodium 1-to-1, so that's not a problem. Put it on. And then for the hydroxide, potassium 1-to-1, not going to change the coefficient. Plug those in. With our spectators, it ends up with 3 sodium chlorites, 4 potassium permanganates, 2 waters, 4 manganese oxide, 4 oxides, 3 sodium perchlorates, and 4 potassium hydroxides. And you should make sure you put the states in to be a complete balance equation. If you look at this, all your atoms should be balanced if you did things correctly. You can see I got 3 sodiums and 3 sodiums on both sides. Got 3 chlorines and 3 chlorines. Okay, we got 4 potassiums and 4 potassiums. I got 6 oxygens and 16, that's 22, and 2, that's 24 oxygens. I have 8 oxygens and 3 and 4, that's 12, that's 20, and 4 more, that's 24 oxygens. Hydrogens would be the last thing. We have 4 hydrogens and 4 hydrogens. So everything's balanced, the balance equation. Should be able to check your answer to make sure things are working. Now at your net ionic, you should be able to check your answer in the sense of atoms and charges if everything's going right. Atoms in this case are all balanced. Let's check charges. I got 3 minuses and 4 minuses. That's a total of 7 minuses. On the other side, I have 3 minuses and 4 minuses. That's 7 minus. Atoms and charges should be balanced on your net ionic equation, which is what this is right here. All right, another experiment we did with kinetics. Okay, you did lots of calculations like this in class, except you did on a concentration base. We kept it as a volume base. And our goal here with this particular question was I just want to know the order of respect to one of the species, meaning B in this case. So you need to do it by inspection, where you can look at things and see if this doubles, what happens to the rate. Does it double? If it is, that's a linear, so that's an order 1. If it goes to the square, it's a 2 power, etc. So we want to look at this data and find a way to eliminate the A. That way I know whatever's happening to the rate is only coming from B. Okay, so looking at this data, we can see that experimental, if I compare experimental 1 and 2, the volumes of the A stay the same, which means the concentration is going to stay the same, but the concentration of B varies. Okay, so I will pick those 2 experiments because whatever happens to A will not affect the rate. Okay, because it's the same in both experiments. So anything that happens to the rate, anything that happens between these 2 numbers is going to be because of B. A has no variant on it because it hasn't changed. So to do this, you can do it by inspection, but then we're looking at some weird numbers here, 10 and 6. It's not easy doubles, etc. So what we can do is take the rate law of one and compare it to the rate law of the other one. I always tend to write the larger numbers in the numerator because I can do the math easier in my head than I can with decimals. So anyway, we'll take the rate. We're trying to find rate is equal to K times the concentration of A to the X times B to the Y is our rate law. And in this particular problem, we're just trying to find the Y. Sometimes you want to find X and K, but in this particular one, I'm just looking for the Y. So we're going to do comparison of our rate laws, and we're going to take experiment 1 and compare it to experiment 2. Okay, I could do 2 to 1 if I wanted. I just like putting the bigger numbers in the numerator. So you basically write in your rate law, rate 1 is equal to K, concentration of A1 to the X times the concentration of B1 to the Y divided by experimental 2, which is your rate 2 equal to K, concentration of your A2 to the X, concentration of B2 to the Y. Plug in the numbers. Okay, we know rate is 6.57 milliliters per minute for 1, when rate 2 is 2.36 milliliters per minute. Equal to K. K is a constant, which is the same in both experiments. Plug in the volumes, which is 10 milliliters for both experiments for A to the X, 10 for experiment 1 for the B, and 6 milliliters for B for the experimental 2. What happens now is my K's cancel, because it's the same. 10 to the X, 10 to the X, I don't care what X is, it's going to cancel. The milliliters per minute cancels, so milliliters cancel as well. So I end up getting this numeric numbers of 2.78 is equal to 1.667 to the Y. Okay, 1.667 is 10 divided by 6. Your 10 divided by 6 is that 1.667, and that 6.57 divided by 2.36 is that 2.78. Now, I need to figure out what Y is, so one way to do that is take the log of both sides. If I do the log to this on both sides, it doesn't change the numeric answer, so I'll do that. So then I take the log of 2.78 is equal to the log of 1.667 to the Y. Now, the reason I want to do this is because I know that if I can take that Y now and bring it to the front and multiply that times the log of the numeric number, Y times the log of 1.667 is still equal to that same value. Now I can divide through by that log. So now I get Y is equal to log of 2.78 divided by the log of 1.667. Here it's important to realize that you can't cancel logs. I can't divide the numeric numbers and then take the log. I have to take the log of 2.78, which is 0.444. I have to take the log of 1.667, which is 0.222, divide them, and get my final answer, which is Y is equal to 2. So it's a second order with respect to B. Sig figs, you got to remember the number of sig figs you have in your log expression. You need that many digits past the decimal. And when you do the antilog, it's the number of digits past the decimal. That's how many sig figs you have in your answer. So that's why my log of 2.78 ends up being 0.444, 3 sig figs, and my log of 1.667, where the sig fig is on that second 6, that's 0.222. Okay, we did an experiment dealing with Beer's law where we're trying to find the concentration of unknown. So here, have a 7 milliliter solution of unknown concentration of cobalt nitrate. It was diluted to 10 mils. So we diluted it. Okay, then we took that sample and we did our experiment with the spec 20 and we found out that the absorbance of that unknown was 0.44. We want to know what is the concentration of that bulk original sample. So to be able to do this, we had to do a Beer's law plot. So you had to do some standards that I knew the concentration of, do the absorbances, and do a plot. Now on the test, you probably have to do your own plot, but I'll go ahead and show you the plot now. So you do a plot. So you do your absorbances on the y-axis and your concentration on your x-axis. These blue little dots were the standards made, okay, on the test. I'll probably give you the standards and you have to actually do a plot. So I have my standards here and I draw my best line. When you come to the test, you should make sure you bring a ruler. That way you can do a nice straight line when you draw your line. From this plot, we can determine the diluted concentration of our sample. And we're going to get that from our given known of 0.44 absorbance for that unknown. So then I got to figure out my axis here. You can see that in this axis up here, here's 0.4. This would be 0.44. This is 0.48, 0.52, 0.56, and 0.6. So you got to make sure you're figuring out how your axis is actually being incremented. Okay, so in this case, it's about 0.04 in this particular case, 0.04 units per line. Okay, so in this case, I'll take that 0.44, go straight line till I hit my curve, and then go straight down till I hit it. Okay, in this case, it lands right on 2.00. Once again, if it was somewhere in between, I would have to figure out how much between and what each one of these lines is worth and figure it out. In this case, it just happens to be right on the mark. Now that is my concentration for my diluted sample. Okay. I want to know for the bulk. That bulk concentration is in that 7 milliliters. Okay, so I got to go back and calculate using CV equals CV to figure that value out. Call the concentration of your bulk times the volume of your bulk equals your concentration diluted times your volume of diluted. We know the volume of the bulk, diluted concentration, and the volume concentration of the diluted. Okay, concentration diluted is what we just calculated. Okay, from the graph. So all you got to do now is rearrange this by dividing by volume of the bulk on both sides and then plug them in and calculate it. So then concentration of your bulk equals your concentration of your diluted times your volume of your diluted divided by your volume of your bulk. Plug in those values. You got 2.00 milligrams per milliliter of your cobalt nitrate, which came from the graph. Okay, remember that came from the graph. We said in our problem that we diluted it to 10 milliliters. That's my total volume. Okay, total volume. Okay, divided by the volume of that bulk, which we took 7 mils and diluted it to 10. Multiply all that out, realizing that my units cancel. Going to leave me in my milligrams per milliliter, which in this case the concentration of my bulk is 2.86 milligrams per milliliter of cobalt nitrate. So important to realize, make a plot, that gives me the diluted amount, and I'm going to have to back calculate using CV equals CV to figure out my actual amount of my bulk, and make sure you're putting your diluted concentration and your volume of your diluted together, okay, in the same spot, and dividing by your bulk concentration. Excuse me, bulk volume. Here's a similar problem, except we're going to go one step further where I want to know what is the actual milligrams. Remember, I'm giving milligrams per milliliter. That gives me a ratio of amount of substance per volume of substance. So I should be able to figure out how many milligrams of particular substance is there. So here I got a vitamin pill, which is crushed and diluted to 500 milliliters in a volumetric flask. Okay, I'm going to take 15 milliliters of that aliquot. Okay, so 15 mils of that 500 we're taking. We're going to dilute it to 100 mils. A 5 milliliter portion of that solution was analyzed with a spectrometer and was found to have a concentration of 4.55 times 10 to the negative second milligrams of iron 2 per milliliter. Calculate the milligrams of iron in the supplement pill. So basically we have some flask, which is 500 mils. I have a vitamin in there. I dilute it and get it in. Then I took 15 mils of that. Okay. And I put that into 100 mils. Then I took 5 mils of that, put it in a cuvette, the spec 20, and I got 4.55 times 10 to the negative second milligrams of iron per milliliter. Okay, so knowing all that, this concentration is that of the 5 mils, but it's also the concentration of that 100 milliliter flask. Okay, so the 5 mils doesn't really matter, just as long as it's past it's enough in the cuvette that the spec 20 is be able to measure it. Because remember, it's only measuring a little slice of that tube, that cuvette. So that 5 doesn't really tell me anything, but this concentration is telling me that of the 100 milliliters. Okay, I want to find out what is the concentration of that 15 milliliters sample that I put into that 100 milliliter. That's just doing your CV equals CV. Okay, so your bulk is 100 mils. Excuse me, your diluted is 100 mils. The concentration is 4.55 times 10 to the negative second milligrams per milliliter. And the volume of my bulk is 15 mils. So let's plug it into your CV equals CV. Okay, in this case we know the volume, that's your 15 mils. We know the concentration, that's your 4.55 times 10 to the negative second, and the volume is 100 mils. Okay, do the math. Means concentration of bulk would be your diluted concentration times your volume of your diluted divided by the volume of your bulk. Which in this case is 4.55 times 10 to the minus second milligrams per milliliter of iron for your concentration of your diluted. The total volume of that diluted is 100 mils divided by the volume of the bulk that made that diluted sample, which is 15 mils. Your 15 mils will cancel. That'll leave you in 0.3033 milligrams per milliliter of iron. So that is my concentration. This is very similar to the calculation we just did in the previous problem. But we want to go one step further in this problem. Okay, we'll go one step further. I want to calculate the milligrams of iron in the actual pill itself. This concentration of 0.3033 milligrams per milliliter is telling me the concentration in that original flask, that original 500 milliliter flask. Okay, it's telling me that concentration. For every milliliter, there's 0.3033 milligrams of iron. I want to know how much iron is in the entire flask. Well, this is a ratio, milligrams per milliliter. If I know that's 500 milliliters, all I have to do is what? Multiply it, and then tell me how many milligrams there is. Okay, because it's a ratio. So many milligrams per milliliter. If I know the milliliters, it tells me how many milligrams. So the next step in this problem would be to take the milligrams per milliliter ratio, 0.3033 milligrams per milliliter, multiply that times my volume. The total volume of that vitamin that was diluted in solution was 500 mils. My milliliters cancel. Leaves me in my final answer that in that iron tablet that I dissolved in that 500 milliliters had a total of 152 milligrams of iron. So this is very similar to what I did in the previous one, except one step further, where we're actually trying to figure out how many milligrams of a particular substance is in that solution. Okay, this one is determining the equilibrium constant. Okay, the experiment was performed on a reaction A plus B gives you C. You're given the initial concentration of A and B. If the concentration of C at equilibrium is 1 times 10 to the negative fifth, calculate K. Okay, so we know the initial of A and B, and we know at equilibrium what C is. We can calculate the K. This goes back to your ICE table. Okay, ICE table. In this case, I know I got 3 times 10 to the negative second, and I have 5 times 10 to the negative second, and we have 0C. Then we let equilibrium goes. We don't know what's going to happen, but we know some of the A is going to change, and we're going to add some C because it's 1 to 1. We increasing on the product side, decreasing on the reactant side. In equilibrium, that means I got 3 times 10 to the negative second minus X, 5 times 10 to the negative second minus X, and X. And we know that to solve for K, K is your ratio of your products over reactants, which would be concentration of C, concentration of B, concentration of B, all of those at equilibrium. So then you would plug these values in. Gives you X, E3 times 10 minus X minus X, and 5 times 10 to the negative second minus X. Okay? But the problem here is I have an unknown, X. What is X? I need to know what X is to be able to solve for this. Okay? Well, is there anything in this problem that allows me to do that? Well, yes. They told me that C at equilibrium was 1 times 10 to the negative fifth. So what is that actually telling me? That is telling me X. Okay? It's giving me X. So all we got to do is just plug that in to solve for our problem. So we know K is equal to the concentration of C over the concentration of B over the concentration of A. So these are all your equilibrium values. Okay. Well, we were given the concentration of C at equilibrium. That's 1 times 10 to the negative fifth. That was given to me. We know that A is 3 times 10 to the negative second minus the X, which in this case is the concentration of C at equilibrium. We know that B is 5 times 10 to the negative fourth minus 1 times 10 to the negative fifth. Okay, will give me my concentration of B. I noticed up here that I said minus 2, it's minus 4. Sorry about that. Okay. Alright, so do the calculation. Get an answer. K is 0.682. Now notice in the future you decided we were able to eliminate X and do our calculation. You can't do that with these K's because those K numbers are relatively large compared to the concentration of our solution, okay? And that X is not very small compared to that concentration we're starting, our initial concentrations. Therefore, you have to include X. So if you neglect X, you're going to get the wrong answer. So you make sure that you have the X, and there's no reason not to. There's no reason to neglect it because you know what X is. And typically in calculations, we try to simplify that by eliminating the X. Okay, they simplify the math. In this case, we know X, so there's no reason to eliminate it. But if you did eliminate it, it's going to give you the wrong answer. Okay, you cannot do that with the K's. Now, when we talk about Ka, Kb, those K's tend to be very small, and we can neglect the X, and it still won't change the answer. Example, I think, is the next one we're going to do. Okay, I have a 0.65 molarity solution of a weak acid HA. Gave a pH meter reading of 2.25. Calculate the Ka of the acid. Okay, so you have a weak acid, HA plus water gives me hydronium ion plus A. Once again, we're talking about an ice table type thing. Okay, so you have some ice table thing here. Got some initial concentration, 0.65, 0 and 0. We got some change. In equilibrium, basically I got 0.65 minus X, X, and X. We know that Ka is equal to your concentration of your hydronium ion times concentration of A minus divided by your concentration of HA. Once again, all these at equilibrium. In this case, you're looking at X, X, and 0.65 minus X. So if I know X, if I can figure out X, I can figure out my Ka. Well, in this problem, is there any way I can figure out what concentration of hydronium is at equilibrium? Yes, I can, because of the pH. When I know the pH, that tells me my concentration of hydronium at equilibrium. So if I know that, then I can plug these in and get to my correct answer. So we know Ka is equal to the concentration of hydronium times the concentration of A minus divided by the concentration of HA, all these being equilibrium values. I need to figure out the concentration of my hydronium, or that X. Well, we know that from pH. Okay, concentration of hydronium is equal to 10 to the negative pH, which is equal to 10 to the minus 2.25. Or if you do the math, will equal to 5.6 times 10 to the negative third molarity. Okay, that is my concentration of my hydronium. Sig fig wise, the number of digits past the decimal. If it's an anti-log, that's how many sig figs I got in my answer. So that is basically telling me that X. Okay, so I'll plug those into my Ka expression. I have hydronium is 5.6 times 10 to the negative third. The A minus is exactly the same number. It's a 1-to-1 ratio, 5.6 times 10 to the negative third. And my concentration of my HA is my initial 0.65 minus 5.6 times 10 to the negative third, which gets me a Ka of 4.9 times 10 to the negative fifth. Now, if you were to neglect the X and say not put this in here, you still get the exact same answer because it's so small compared to that. And that's basically because the size of your Ka is so small, 10 to the negative fifth. Okay, while typically with your Kc problems, their Ks are larger than 1, you know, greater than 1, some numbers, you know, 20, 30, 40, 50, whatever. Large numbers of K, it's not going to be a case that you can neglect those X's. You're going to need to put them in there as you do the calculations. Okay, based on the preparation of alum, that's your potassium aluminum sulfate dodecahydrate, from solid aluminum, determine the percent yield of an experiment. Okay, so here they said we start off with 1.1 grams of aluminum. At the end of the experiment, after doing all the filtering, etc., they came up with 9.56 grams of alum. Okay, so we're trying to find out percent yield. Percent yield is your experimental or your theoretical, time 100%. Experimental, we already got. They gave me that. Now I got to figure out from here my theoretical alum. Okay, so I got to take those grams of aluminum and change it into grams of my alum. So we start off with my grams of aluminum. To get from one substance to the other, we always know we got to go through moles. So I'm going to go through molar mass of aluminum, which gives me 26.98 grams of aluminum for every 1 mole of aluminum. So my grams cancel. So now I got to get from moles of aluminum to my alum, and that ratio is 1-to-1. For every 1 mole of potassium aluminum sulfate dodecahydrate, there's 1 mole of aluminum. Now, on the quiz, I noticed some people tend to do a 2-to-1. You got to realize it's 2 aluminums for every 2 potassium aluminum hydroxides, and then it's 1 potassium aluminum hydroxide to every 1 alum. Okay, which basically means it's a 1-to-1. Okay, 2-to-2 and then 1-to-1. That cancels out to a 1-to-1 ratio. Or the simplest thing is look at it. Inside of your alum, okay, how many aluminums are in there? 1. Okay, so it's in that ratio as a 1-to-1 ratio. Now that gets rid of my moles of aluminum. So now I want to get from moles to grams. So molar mass of my alum, which is 474.44 grams, and make sure when you calculate the molar mass that you include those waters. Okay, multiply that out. It gives me 19.34 grams of my alum. That is my theoretical. That's how much I should actually get. Okay, we don't always get what we're trying to do experimental. Okay, you lose product, etc. So then we have to do our percent yield, which is your experimental divided by your theoretical time 100%, which in this problem was 9.56 grams of alum divided by your theoretical, which is 19.34 grams, multiplied by 100%. So you multiply by 100, which then gives me 49.47%. Okay, if you have any questions or need any help with any of these calculations, feel free to stop by my office. I'll be more than happy to help you. I hope you enjoyed the class. Wish you success on your finals. I also wish you success on your careers. If there's anything I can help you with, feel free to stop by my office and see what I can do for you.